Good afternoon, everyone. I just want to give you a little review on some things with Le Chatelier's principle and equilibrium and make sure that you're understanding the basic principles before we move on to the next chapter. So again, here we are talking about that if we have our rate on our y-axis over our time, we can understand that if I draw something like this, that those would be representing of my reactants because they would be decreasing over time. This would be my products because they would be building up over time. And again, we want to make sure that we understand that this equilibrium expression or equilibrium position has been defined. And so here's my equilibrium position, but at this point now, my reaction rates are equal. And keep in mind again that our K constant is equal to our concentration of our products over the concentration of our reactants. And the only substance we put in here are gaseous substances. Our solids and liquids are not going to change this equilibrium expression. So we're just trying to give an insight on these. If I take a look, I have another little example here for you, that if these represent my reactants and this represents my products. So obviously it looks like I have a very small amount of reactants and a large amount of products, and I am reaching equilibrium. What does this say about K? Well, in this situation, my equilibrium shift lies to the right, as you can see by the buildup of my products, and your book uses a sign like this, that my K, they're just saying that my K is much, much greater than 1. So it's just talking about our equilibrium constant to help us describe the reactions and give us some insight about the concentrations. So again, if I say that this is my reactants, and so I have a lot more reactants than I have products, and I have reached equilibrium, my equilibrium favors the reactants, and what that is saying then is that my K is very, very small, much less than 1. Okay, moving on to another example here, just to show you, I drew some boxes with some dots and some stars, because you guys are all my stars. And what I want you guys to do is I want you to rank these in order of increasing K. So increasing K, and each one of these I've held constant that there is 10 here. And if we call this box A and box B and box C, or reaction A, B, and C, and we could say that my circles are at equilibrium with my stars, and that would be my scenario for all of these, that my circles, my yellow circles, are at equilibrium with my stars. If I was really fancy, I'd put those up there for you, but sorry, a little short of time, so some of these things are going to be some crude little examples here because I'm quickly trying to do this before my family arrives at home and there's all kinds of chaos around here. So if we take a look that we are at equilibrium, excuse me, you can see that if I'm putting these in order of increasing K, this is going to be the smallest because this is favoring my reactants. Then I would go to A because I would have a few less reactants, and then as I would, my last K would be C because this is greatly favoring my products, and that would be the largest K that you have there. Kind of going on to the last slide that I just gave you about K and how it is predicting that if it's favoring, and if it's favoring my products and it's lying to the right, then my K is going to be very large. So what does this say a little bit about position? So position of equilibrium, where equilibrium is established as the reaction progresses. So if I have a small K, you need to be thinking about that my equilibrium is established very early in the reaction process. It happens pretty quickly. And if I have a very large K, my equilibrium is established very late throughout my reaction process. So this would be a very large K. There's a difference in the rates. For instance, a large K if a car is rusting versus explosives. They both have a very large K, but it's their rates in reaching the equilibrium that's going to be very different. So if we take a look at our equilibrium constant, what does that do for us? It helps us predict the direction the reaction will go to achieve equilibrium. Remember that if you are an engineer, you are really looking at this direction of the reaction because you want to maximize the products. and it also helps us calculate the concentration of the reactants and the products when equilibrium is reached. Okay, one more little scenario that I have here for you to take a look at is we talked about K at equilibrium in regards to Q, which is our reaction quotient, which varies as the reaction proceeds. So we're just going to use this to compare. So if I take a look that this is K and this is Q, sorry I didn't get in there very well, and this is going to be Q and this is going to be K, and these are just representing products and reactants again, that if this is K and if this is Q. So if I take a look, remember in each of these situations, it's always my equilibrium expression is my products over my reactants. So if I take a look at this where Q is much smaller than K, my reaction shift is going to be to the right. I have too much reactants. So again, if I take a look at K, remember it is the concentration of my products over the concentration of my reactants. Well, if I have this scenario, I have Q that's smaller than K, I have too much reactant. I have too much of this, and so I need to shift it to the other direction. Here they're obviously equal, there isn't going to be a shift. And then here I have too much product. I have that my Q is greater than my K, and so this is going to have to shift in this direction to reach equilibrium. So again, my product, there's too much here. It's way too large. Okay, and the last thing that I'd like you guys to do is I want you to pay attention to this equation that I'm going to write for you and apply Le Chatelier's principle. So if I have hydrogen gas and I have iodine gas, which is also diatomic, and it has reached equilibrium, I will have 2 moles of hydrogen iodide in the gaseous phase. All right, so my first question is going to be if I'm applying Le Chatelier's principle and I add more of this. If I add more H2, which way is my shift going to be? Hopefully you said right before I did. If I add more I2, I'm adding more of my reactants, which way is the shift going to be? Correct again, it's to the right. I'm confident that you figured that out, and so my equilibrium needs to shift to the right to reach it. And this time I'm going to add more of this. What is my equation going to do? My equilibrium is actually going to shift left. You're exactly right. So it wants to shift away from the addition of the concentrations. Okay, let's do the opposite. Now I'm going to remove my HI. Hopefully you said it's going to shift to the right. Le Chatelier's principle says that it's going to shift in the direction of the removal of the concentration. Okay, this time I'm going to add some helium gas. What is that going to do? Hopefully you're thinking nothing, because this is an inert gas, it's a noble gas. There's not going to be interactions, it's not going to affect the equilibrium at all. All right, how about if I decrease my volume? If you're decreasing your volume, you should be thinking about the number of moles of gas that you have on both sides. You can see that this is 1 plus 1 is 2, and this is 2. So they are equal on both sides, so there will be no shift in equilibrium. Okay, well hopefully these few little points will help you apply some things that we've learned in this chapter. Have a wonderful night.